a PQ. And what does it mean physically? That here we have the space given by Q and P. Okay? So we have a manifold M, which in our case is R2. And the Hamiltonian equation define a flow minus dH with respect to Q, and then the T equal plus dH dP. So this Hamiltonian equation define hydrodynamic flow in R2 given by the velocity field uv equal the p the t, the q the t, which is equal to minus plus q and p plus dH dP and minus dH dQ. So what does it mean? At any point in R2 I will have a vector field V, and this vector field V at any point will define a flow, and so at any point P the tangent to the trajectory will form a velocity field V, and this velocity field is has a special property. This velocity field is incompressible. V is incompressible, which means that the divergence of V is equal to 0. So what does that mean? If I start with an initial volume of water, this volume deforms in time, but it doesn't change. Okay, the volume will always stay the same. That's what does it mean for this divergence to be 0. And actually, this divergence, for the divergence to be 0, what does it mean? It simply means that let's the divergence, clearly divergence with respect to the Q, the P, with respect to this basis or gradient with respect to P and Q. And that is very straightforward to prove, because we already have the expression of the divergence of the flow of the velocity field, which is given by these quantities. So we need to impose that, we need to show that the U, the Q plus the V, the P is equal to 0. But these are equal to what? Partial with respect to Q of dH dP. Minus partial of P of okay, the U, the Q is equal to this plus the partial with respect to P of V, but V is minus dH dQ, minus dH dQ. And as you can see, mixed derivatives are identical, and this is basically equal to 0. Okay, so an Hamiltonian flow, an Hamiltonian equation generates a pseudo hydrodynamic flow in the variable P and Q, and the dynamics, the flow evolution, it is in such a way to keep the flow incompressible, and so the area in the area of patches of areas evolve under the flow by keeping the area constant. And so that is one of the main properties of an Hamiltonian flow. In this case, using differential geometry jargon, the form, the Q cross the P, is conserved. Okay, and of course, in this case, the Hamiltonian was given by the total energy, but there are other examples in which not necessarily the Hamiltonian is the total energy, and a simple example is given from fluid